All right, so today we're going to do volumes of revolution. Again, I've talked to a lot of fellow calculus teachers about this, and after thinking about it for a long time, I realized that some of them are teaching it like volumes of revolution are completely different than volumes by slicing, which is the wrong approach. Okay? They're the same thing. Now, how you get your slice is different, but that's the only difference. So, another type of volume problem involves revolving a region in the xy plane about a line to create a three-dimensional solid. Again, it is not important that you can visualize these three-dimensional solids in your head. I can, but I used to teach it that way, and I'm really good at spinning things in my head and seeing what they look like. Okay? Spatial visualization is one of the things that I'm naturally good at. There's not a lot of them, but that's one of them. So the cross section of these solids will either be a circle or an annulus every single time. So anytime they say revolved about this line, you know it's going to be either an annulus or a circle. How do you know which one it's going to be? Well, again, you can try and visualize it, or you can just look at this. If your representative slice here is attached to the axis of revolution, so that's like this. This pen is stuck to my finger. I'm going to point the line at you. When I spin this around, what am I going to get? A circle, right? There's no gaps anywhere. But on this one, notice there's a gap between my representative slice and my axis of revolution. So again, that looks like this. My pen is way up here off of my finger. Now if I point this at you and I spin this around, I have a circle with a hole in the middle, right? That's an annulus. That's all you have to understand. So if every one of my slices is attached to the axis of revolution, every slice is going to be a circle. And if none of them are, except for sometimes on the very end, it'll touch in one place, but it still works. If you have slices that are not attached to the axis of revolution, when you spin it around, you get an annulus. You've got a hole in the middle. Okay? So that's how you tell what does my slice look like. So on the other ones, they tell you what your slice is. Here, you have to figure out, is my slice an annulus or is it a circle? It's always one of the two. Okay? That is the only difference between these problems and the ones you were doing last night. So remember that for a circle, the area is pi r squared. And on this, let's go ahead and fill this in. The radius is going to be here. That's your r. On this one, remember we're spinning around this line, right? So I'm going to have two different radii. I'm going to have the radius of the inside circle, that's the hole, that's little r. And the radius of the outer circle, that's big R. Okay, now, I will say occasionally the line is on top. Still works the same way. Okay, and we'll look at one like that, I think, in just a moment. So let's do some examples. So find the volume of the solid formed by revolving the region bounded about the x-axis, the graph of y equals the square root of x, and the line x equals 4 about the x-axis. So let's sketch that. So square root of x is all in the first quadrant anyway. So y equals the square root of x looks something like that. The x-axis is down here. X equals 4, somewhere over here. So that's my region. And I will sometimes go back and just briefly go outline it. Or if you've got a highlighter, outline it. Something like that. That's my region. And then I need to know, well, what am I spinning this around? Well, I'm spinning this around the x-axis. And that's not a G, that's supposed to be like a circle with an arrow. This is spinning around. Notice my axis of revolution is one of my boundaries. So that means that every cross-section that I take is going to be attached to my axis of revolution. So when I spin this around, am I going to get a circle or an annulus? Circle. We're going to get a circle. And this is going to be the radius of the circle. So this point is going to be some random x coordinate, and the y coordinate is going to be the square root of x. This point will be some random x coordinate, and the y coordinate will be 0. So what's the area of every cross section? Well, it's a circle. So what's the area?
Pi radius squared.
Exactly. And what is the radius going to be in terms of x?
Square root of x.
Yeah, because it's the square root of x minus 0. Always be thinking about subtracting. Some of the ones we're doing right now are easier, and people sometimes freak out when this is something else. Always think about it's the upper one minus the lower one. Or if you're slicing perpendicular to the y-axis, it's the one further to the right minus the one further to the left. So the radius is going to be the square root of x. So the area in terms of x is pi times the square root of x squared. So it's just pi x. So then the volume is the integral. Where do we start slicing in terms of x?
0.
And where do we stop?
4.
Right. Pi times x dx. Take the antiderivative. This will be pi times 1/2 x squared from 0 to 4. So that's 8 pi.
So mathematical.
It is. Any questions about that? All right, let's go to this next one. Revolve the region from the previous example about the horizontal line y equals 3. What is the volume? Okay, let's take a look at that. So again, I'm only in the first quadrant. Y is the square root of x, is this half of a parabola. X equals 4 is over here. So this is my region. And I'm now revolving this around the line y equals 3, which is somewhere up here, right? Is that one of the borders of my region?
No, it's annulus.
So it's going to be an annulus. I mean, it really is that easy. Is your axis of revolution one of your borders? Then you're going to get circles. If not, you're going to get, I don't know if annulus is annuli or annuluses.
I would say annuli.
Seems like it. Okay, so I know that my area is going to be pi times big R squared minus pi times little r squared. If I take a representative slice here, the coordinates of this point are some random x coordinate and 0. The coordinates of this point are the same random x coordinate and the square root of x. And the coordinates of this point up here are the same random x coordinate and 3.
So it would be 5 3 squared minus.
Wait. What?
Would big R be with 0?
The big R would be yes. It's going to be 3 minus 0. Little r will be the distance from here to this point, which is going to be what?
3 minus the square root.
Yes, 3 minus the square root of x. So the area in terms of x is going to be, when I square the 3, that'll be 9, so 9 pi minus pi times 3 minus the square root of x squared. Now, this one is doable by hand. I'm going to go ahead and do it by hand just to kind of show you how it works. Most of the time, these are going to be calculator active, right? Not all the time, but most of the time. But this is doable by hand. I would want to simplify this sum. This is going to be 9 pi minus pi times, when I square this, that's going to be 9 minus 6 square root of x plus x. Notice that when I distribute the pi and subtract, I'm going to have a 9 pi minus 9 pi. How nice is that? So we're going to have 6 pi square root of x minus pi x. So the volume will be the integral. We're slicing perpendicular to the x-axis. So in terms of x, where do I start and where do I stop?
0.
Right? Of 6 pi x to the 1/2 minus pi x dx. So that'll be 6 pi times 2/3 x to the 3/2 minus pi times 1/2 x squared, all from 0 to 4. Let's see, that's going to be 6 pi times 2/3 is 4 pi times 9 to the 3/2 is
No, 127? Should it be 4 to the
oh sorry 4 to the 3/2. My fault. 4 to the 3/2 is
32.
pardon?
Wait, is it like
64.
4 cubed?
Now wait, hold
Oh
on.
gosh.
It's 4
Okay,
It's
don't cube it first.
It's 8 then.
Take the square root first, then cube it. It's always easier. We talked about this before.
That's what I was doing, and he started yelling out 32. I was so confused.
This is 8.
Would 9 to the 3/2 been 27?
Yes.
Got that one right.
And this will be 16 times 1/2. This is 8 pi. So this is 32 pi minus 8 pi is 24 pi. Okay, one more on that same track. Revolve the same region about the vertical line, x equals -1. Okay,
Scale roots.
So we've got y is the square root of x equals 4. That's my region. So I'm going to outline it just a little bit. And then I've got the vertical line, x equals -1. I'm going to do that in a different color. X equals -1 is over here. Okay. The other thing to notice about these is it doesn't tell you where to slice it or how to slice it. It doesn't tell you whether you should slice perpendicular to the x-axis or perpendicular to the y-axis. For our purposes, and because we're not going to learn, there's an extra thing you can learn that's not on the AP exam. I taught it to my BC students, but I'm not going to teach it to you guys. You don't have to know it for the AP exam. Make your slices perpendicular to the axis of revolution. Okay, so you want your slices to be perpendicular to the axis of revolution with what you know. That means that my slices are going to run this way. So I want everything, and that's also perpendicular to the y-axis, right? Mm-hmm. So I want everything to be in terms of y. So I had y is the square root of x. Well, that means that x is equal to y squared. And where these intersect up here, when x is 4, what is y going to be? Try again.
2.
Y is going to be 2. So is my axis of revolution, which is over here, one of the borders of my region? No. So what am I going to have? An annulus. So the area is pi times big R squared minus pi times little r squared. What is big R going to be? Well, it's the distance from here to here. Let's do like we did before and let's put all those points in. So now this is going to be x is 4 and it's going to be some random y coordinate. Over here, x is y squared. So this is going to be y squared, again, comma, some random y coordinate. And this coordinate is going to be x is always -1 there, and it's the same random y coordinate. So now the big radius is the distance from here to here. Well, that should be 4 minus -1 is 5. And the little radius is the distance from here to here. So how can I write an expression for that?
Y squared plus 1.
Yeah, y squared minus -1, which is y squared plus 1. So then the area in terms of y is going to be 25 pi minus pi times y squared plus 1 quantity squared. And because I'm not going to take the time to do this one, I'm not going to bother squaring that and simplifying. So then the volume will be the integral as y goes from what to what?
-1 to 4.
Both wrong.
From 0 to 2.
From 0 to 2. Right? -1 to 4 is what x changes from. Y changes from the bottom here, which is y is 0, till I get up to here where y is 2. of 25 pi minus pi times y squared plus 1 quantity squared dy. And in the interest of time, I'm not going to finish that one. All right, let's see what we can do with this one. This is definitely going to be a calculator problem. The region R is bounded by the graphs of y equals x squared and y equals the natural log of x plus 1. Find the volume when we revolved around the y-axis and the horizontal line y equals 1. All right. So, let's see if we can get at least one of those done. I don't think we'll have time for both. Y equals x squared, that's just a simple parabola. Y equals natural log of x plus 1 is going to look something like this. Oh, except it's going to go through at 0. Because normally it goes through at the x-axis at 1. So move to the left one space, it'll go through at 0. So this is my region. All right, and we want to revolve around the y-axis. So which way should I slice? Well, you said perpendicular to the x-axis, but the way you're holding your arm is not perpendicular to the x-axis. So, yeah, so perpendicular to the y-axis. That's going to be my typical cross-section. So I already know what the area is going to be. The area is going to be an annulus. It'll be pi times big R squared minus pi times little r squared. I need everything to be in terms of y because I'm going perpendicular to the y-axis. So, okay. So that's going to be x is what? The square root of y. And here, that's going to be e to the y equals x plus 1. So it'll be e to the y minus 1 is equal to x. So when I put my points on here, this point, again, that's some random y coordinate, but the x coordinate is the square root of y. For this point, again, it's some random y coordinate, but the x coordinate is e to the y minus 1. And this coordinate is 0y. The big radius will be the distance from this point to this point. That's changing in x, right? So it'll be the x coordinate minus the x coordinate. It's just the square root of y minus 0. The little radius will be the distance from this point to this point. Again, that's a change in x. So that's e to the y minus 1 minus 0, which is just e to the y minus 1. So my area in terms of y is pi times the square root of y squared will be y minus pi times e to the y minus 1 quantity squared. So then the volume will be the integral from, well, this point is 0 in terms of y. We'll have to find that one in just a second. Of pi y minus pi times e to the y minus 1 quantity squared, all dy. And now we got to find out where those two intersect each other. So y is x squared, and y is equal to the natural log of x plus 1. Let's clear that out. Natural log of x plus 1.
I got that. They intersect
They intersect where?
at 0.5578323. Like that's the y value.
Okay. I will take your word for it. Point what?
5578.
I don't need any more.
And for my final answer, I got 0.206.
Okay. Since the bell's going to ring, I'll trust you on that.
Our quiz tomorrow is over what we did yesterday and then the weekend.
And the area, yeah. So it won't include any volumes of revolution.